Experimental and theoretical study of the heavy vehicle dynamics loads on terrain. Abstract. It is well known that there is a strong connection between wheel loads of heavy moving vehicles and the behavior of the soil. This relationship can be entirely determined if the stress in the soil for heavy car loads and soil conditions are correctly defined. A mathematical model to predict the heavy load, dynamic and static, of the wheel on soils was implemented in this paper. In addition, under the floor surface, the vertical, the radial and tangential stresses showed different values of soil depth and different soil types. The insufficiency load was described by experimental laboratory experiments using 5 soil types. The required soil, which could be used without fail for the heavy vehicle motion, could be chosen from experimental and theoretical results. Keywords: heavy vehicle, dynamic wheel load, random input, soil stresses and soil properties. Introduction. A large number of off-road equipment moves over the terrain. In view of the number of tractors and agricultural soil growing equipment used, the number of earth-moving machines used in the construction industry, the number of off-road lorries used in the off-road transportation industry, and the number of military vehicles used for combat and logistic purposes. One of these devices can understand the degree to which mechanics are applicable, as they are concerned with soil stress below ground surface as a result of the movement of off-road devices. The loading of the wheels, dynamic load exerted by a tire, the weight distribution, static load, is critical to the performance of the heavy vehicle. There is also evidence that this load influences ground tension under the pneumatic. One cause of the pressure on the building and the downward collapse of the building is the stress distribution below the land area because of both the impact of wheel loads on the earth and the transported load effect at different depths of the soil. The accurate prediction of the soil stress is a complex issue, taking into account the dynamic wheel load, the various soil types, various soil layers and soil water. A large number of studies concern with the study of stress distribution at contact area between tire and soil 1 to 5. Nankali et al. 6 studied the effect of dynamic load on soil stress analysis of tractor tire interacting with soil using 2D finite element method. Howley and Christian Schindler 7 presented the analysis of soil compaction and tire mobility with finite element method. Also, road vehicle suspension design, dynamics, and control by Dongpyo Cao et al. 8. Agostinaccio et al. 9 presented the vibrations induced by surface irregularities in road pavements. In the light of the previous available researches in this field, it can be said that very little information is available on soil stresses distribution below terrain surface. So, the main objectives of this research towards to develop a mathematical model for the heavy vehicle and the terrain properties. This model used to predict the heavy vehicle wheel loads, dynamic and static, affect terrain surface. To estimate the soil stresses, vertical, radial, and tangential, resulted from the effect of wheel load over different types of soil and at different soil depth. To carry out laboratory tests to measure the failure load of selected 5 types of soil and to evaluate the stresses in soil under the measured failure load. To select the best suitable soil, with which the heavy vehicle can be moved without soil failure. The heavy vehicle dynamic model. The Fig 1 shows an 8-degree schematic diagram. The model for 2-axled heavy-duty vehicle ridings consists of 3 masses connected by linear spring and damper elements that create dynamic forces based on their relative positions and speeds. Also, the tires, Sharp, RS and Corolla, DA, 10, were modeled as linear vertical spring and damper. The model has 8 degrees of freedom based on the second law of Newton's motion. It is represented by the steady state of a vehicle in order that, because of the static deflection of the suspension components, the effect of mass gravity conditions can be lost with forces. The 8 degrees of freedom in the model are representing to the bounce movements of the driver seat XDS, the 4 road wheels. Inputs to the model take the form of wheel displacements generated by the vehicle traversing over a ground profile. These inputs are independent so that, a rear wheel input is simply a delayed version of a front wheel input, and near side inputs may be correlated by an amount dependent on their distance apart. An artificial road input time history x 0 tons of the road profile can be generated from the spectral density function PSDF of a given road by using digital processing involving the inverse discrete Fourier transform, Ruff 11, Robson 12 and Sieben and Newland 13. The road noise function is where F is the frequency, up to 15 Hz, C is the road roughness constant and V is the forward vehicle speed. The heavy vehicle model moving over terrain soil is solved as a nonlinear because the soil deformation sinkage Zk, T, created during the heavy vehicle movements over the terrain profile. The soil deformation sinkage produced under wheels calculated here by equation 10. The generation of the artificial road input time history x 0 tons of the road profile could be used directly as input to the front wheels. The rear wheels running behind the front by a lag time LT. Subtracting the total soil deformation sinkage from the road profile, will modify the rear wheels input as the following equation. Stress distribution in soil. A large proportion of soil engineering problems require an understanding of the soil stress behavior. Also, the analysis of the relationships between applied load and contact area, soil depth, and settlement due to applied load is one of the key problems of the land relative to applied loads. In fact, these relationships are very complex with regard to the soil characteristics and to different load values. In this area, the theoretical studies have included a number of hypotheses to simplify the understanding of this phenomenon. The stress below the surface of the ground is due to the soil's self-weight and load. The effect of heavy car wheel load on the soil stresses is investigated in this paper. The overall static load of the wheel is expected to be the results of the distribution of weight and the maximum dynamic load on the wheel. The Boussinesq theory of stress helps with this assumption. The theoretical results of elastic theory in the most basic case of loading acts on a solid, homogeneous, elastic, semi-infinite, and weightless medium are used to support this theory. The charge is vertical, pointing, on the horizontal boundary surface, in this case, road surface. Radial distribution of stresses in the semi-infinite medium is assumed in one and only concentrated load. The assumptions of Boussinesq are that the earth is weightless, the soil is stress-free before the effect of pointing, stress continuity, and stress symmetrical axis. The pointed load of the semi-infinite mass surface is shown in figure 2. The following equal parameters include the vertical stress on a horizontal plane, radial stress, and tangential stress 14. The above equations shows that the vertical stress depends on the ratio of Poisson, while the radial and tangential stresses depend on the ratio of Poisson. Testing mold and loading system. The model consists of a 30 cm long, 30 cm wide, and 30 cm high stainless steel box. Mold materials wall thickness is 10 mm. Static loading with a rigid footing was the loading method used in this analysis. This foundation had a width of 5.7 cm and a length of 7.1 cm. It reflects the wheel truck dimensions of the selected magnitude. The base was fixed to a steel rod of 5 cm in diameter and 20 cm in height and soldered at the top of the rod to a circular plate of 10 cm diameter and 2.5 cm thick. This method ensures that the load over the footprint of 5.7 to 7.1 cm is spread. The charge was measured with a 300 knots compression machine with a precision of 0.1 kN. Fig.3 displays a complete configuration of the model. Materials used. A number of bearing capacity tests were performed in laboratory on 5 types of soil to analyze the load applied, contact area, soil depth and settlement of soil due to the applied load. In the present experiments 5 types of materials have been used. Silty clay, coarse sand, stoned lime, sandy gravel, and gravel sand are the forms. These soils are used on the unpaved road as base layer. Tests were performed to determine the physical characteristics of these soil types. Figure 4 shows the grain distribution curves and Table 1 shows the physical properties measured for the various soils used for the experiments. Experimental program and procedures. In the experimental program of this study, we measured the load of failures, ultimate load, that can be performed in the base course samples. All of the experiments have been conducted using an automating compactor to compress the base layers in the model with optimum dry density Dmax and optimal moisture content, O.M.C. The modified Proctor compaction tests were carried out at the laboratory to determine the values of OMC for each sample. Each layer equal to 5 cm, the soil is compacted in the model. Compact soil finished at 20 cm thick. A compression testing computer was used to statically load. At a constant load rate of 0,5 kN/min, all tests were completed. The deformities were measured with a 25 mm dial gauge and 0.01 mm accuracy and were also automatically measured with the measuring system. Results and analysis. To solve these models, there are 3 computer programs using MATLAB software. The first software is designed to get time domain road input and figure 5 displays the soil input spontaneously in the history of the front wheels, while the road under the rear wheels shifts like equations. 10. The parameters for the road formula are 15 Hz frequency and 5*106 road rugging. The second software is designed to obtain variable randomly dynamic loads of wheels, and an example is given in the figure 6 for the proportion of the dynamic force for wheels for front wheels. The third program consists of the equations explained in the stress shifting portion of the soil under the terrain surface. The results of different tests are shown in Fig 7, which gives the relation between the applied load and the settlement associated. As shown from Fig 7, the sandy gravel soil gave the higher value of load with settlement compared with the other types of soils. Also, from the figure it can be seen that the value of applied load was increased with settlement without peak value for sandy gravel soil, limestone soil, and silty clay soil. For case of using gravelly sand soil, and coarse sand soil, the load peak value was obtained as shown in the figure. As a conservation of the 2 direct portions of the applied load settlement curve, phi load, was taken as the intersection as illustrated in Fig 8, or in case of the full load, the maximum load value. Figure 9 shows the failure load values for the various types of soil used. Lime, sandy gravel, raw sand, HEPA, and stubborn clay, 56, 75, 8, 13.5, and 4.5, have tons failing at Kn. Based on the findings in Fig 9, it can be said that sandy gravel soil is the highest, then calcareous gravel, and gross sand, and silty clay soils are the worst soil. With a static and dynamic impact of wheel load, heavy vehicle movement projected stress on the ground and shown in figures 10 to 13. Figure 10, A, B, C, shows the distribution by horizontal distance from the vertical axis of the tire, of the vertical, radial, tangent stresses at various Poisson values of the ratio. The ratio of Poisson ranged from 0.2 to 0.5 m at ground depth, and 15 knots was caused by the movement of heavy vehicles over sand soil. The vertical stresses do not differ from the pneumatic vertical axis in the horizontal span, whereas radial and tangential stresses in the soil vary. The radial stress has increased by increasing the Poisson ratio, while the tangent stress is increased to around 0.63 m and decreased afterwards by increasing the Poisson ratio. The radial stress has increased. The distribution of stresses in the soil with the adjustment of the ratio of Poisson along the depth of the soil at a horizontal distance of 0.3 m is shown in Fig 11, A, B and C. The horizontal distance effect on soil stresses can be seen in Fig 12, A, B, and at Poisson, the horizontal distance ranged from 0,2 m to 0,6 m and sand. The vertical stress is decreased while the radial stress increases as the horizontal gap is increased. The direction of the highest stress peak is also modified with different amounts of horizontal distance. Fig. 13, A, B and C, presents a horizontal distance to distance from the vertical tire axis for distribution of stress on soil at varying values of soil depth. At the Poisson ratio of 0.3, Soil depth ranged from 0.6 m to 1.2 m and stress on the sand surface. The figure shows that the vertical stress and radial stress decrease as the soil depth increases, while the tangential stress increases with the soil depth and decreases after a horizontal distance of about 0.63 m. The results of experimental work compared the wheel load value of 15 knots to the soil of the heavy vehicle obtained from theoretical work were achieved. The results were calculated. It can be seen that the heavy vehicle used can be driven across sandy gravel and calcareous soils without any soil loss, while the soil will fail with the hefty vehicle movement in the case of coarse sand, HEPA, and silty clay. It is safe to assume, therefore, that sandy gravel soil is the best soil. Conclusions. The model developed gives the historical wheel load effect to soil stresses. The ratio of Poisson affects the radial and tangential stresses clearly. As soil depth and the horizontal distance from a vertical tire axis increases, the vertical stress decreases. On the basis of theoretical and test performance, the heavy vehicle used can be driven over the following soil types without soil insufficiency: sandy gravel soil accompanied by limestone. It is safe to assume, therefore, that sandy gravel soil is the best type of soil.